Okay, in this video, we will talk about resampling methods in statistical learning. Okay, so we will try to see what is resampling methods is basically, and we will try to see different kinds of resampling methods we can use in machine learning, and the most important question is why we need resampling methods. Okay, now before we start jumping onto that one, let me try to define what is resampling methods is. Okay, then we will try to see why we need it. Then we will try to see some of the different varieties of resampling methods we have in our in statistical learning. Okay, now by definition, resampling methods we can define in something this way, like by repeatedly. Let me try to define it first, then I'll try to explain it. Okay, repeatedly drawing samples, drawing samples from a training data. Okay, from training data or training set, and refitting a model or machine learning model of interest on each sample. Okay, on each sample in order to obtain additional information about that fitted model. Okay, in order to obtain additional information about the fitted model. Okay, so in order to obtain additional information about the fitted model. Okay, now let us first try to see why we need resampling methods. Now if you see my previous videos on linear regression or logistic regression or decision tree or KNN, right? So over there what we did, like we had a training data, and then we just fitted that model, that machine learning model only once, right? Try to get a to get a basically fair good amount of prediction over there. Now in case of resampling methods, according to this particular definition, so what we are basically trying to see it over here, like we are basically fitting the machine learning model more than once, right? So we are basically drawing sample from the training data and then fitting the machine learning model once, but more than once basically. So why we need to do that one? So there are multiple reasons behind this one. Okay, so let us try to reason through it, like why we need these resampling methods. Okay, let me change the color. So why we need resampling methods? Okay, now there are various reasons behind this one. Okay, now the first reason could be, like if you remember from my previous videos when we talked about the machine learning model performance, right? So over there we talked about various measurement by which we can measure whether this particular algorithm is best suitable for our input data or not, right? And while doing that, we discussed the term called MSE, right? mean square error, right? So let me write it down. Mean square error, right? And while doing that one, we also talked about two different terms over here, right? Test MSE and the training MSE, right? And while doing that one, we also talked about, like, finding the test MSE will be very much difficult because we do not have the test data available beforehand, right? A very good amount of test data available before, and if we talk about real life scenario, right? So for that reason, in statistical learning or machine learning, we need to have some way by which we can measure this test MSE, because if you remember from that video, we saw an example where if you train a particular model and calculate that particular training MSE and test MSE, training MSE is does not basically is it's not a good measurement of the mean square error, because we are still measuring from our training data itself, right? And in real life scenario, the test data could be somewhere different from the training data itself, right? So test MSE is actually the good measurement of model performance. So, and the main problem is we do not have the huge amount of test data in our hand beforehand, right? So for that we need a way to measure the test MSE from the training MSE as well. Okay, so resampling methods can help us to find that one, to at least to some way to measure that one. Okay, so this could be one need by which for which we need to study the resampling methods. Okay, now let's talk about another scenario. Now when we talked about linear regression over there, right? So for the input data, we already assumed that our data is linearly distributed, right? So that means we can draw a line through that data, and then we can do fair amount of prediction over there. But in real life scenario, the input data may not be linearly correlated, right? So it could be like it can either follow some quadratic equation, or it can follow some kind of other higher order equation as well, right? So in those cases, so there is a need that we need to find a proper machine learning model, a proper I'll just write ML over here, ML model for the given data. Okay, for the given data, that means like whether it could be a linear model, okay, by linear regression, or it could be a non-linear model, right? Whether it's a linear machine learning model or non-linear machine learning model, we need to know that one, right? Now resampling methods can help us in those scenarios as well, right? And this particular method is sometimes, this particular method is called model selection as well. Okay, so model selection. Now another important use case of resampling method could be like, if you remember from my video on decision tree, right? Over there we discussed like, if we have very huge amount of features in our data, right? And we have various samples in our data, and which we will be having for the machine learning model to work properly. In that case, there is a tendency of decision tree to overfit the data, right? That means decision tree will grow much faster. So in those scenarios, there was a need like we should be controlling the decision tree growing, right? So there are various methods we will be seeing in future videos as well. There are various methods we can see for the decision tree, like random forest or bagging, boosting, those algorithms. Okay, now those are heavily influenced by the resampling methods. That means resampling methods basically act as a base for those kind of algorithms. Okay, so if I just say accuracy of the parametric estimate. Okay, so sometimes this kind of methods are called bootstrap as well, STRAP. Okay, so we will see in next video we will talk about bootstrap. This video will talk about another resampling method called cross validation. Okay, let us now talk about different types of resampling methods. Okay, so let me change the color. Okay, types of resampling methods. Okay, so there are basically two different types of resampling methods we have. One is, as I told, cross validation. Okay, and the second one is bootstrap. Okay, now cross validation generally help us to deal with this first two kinds of problem. MSE wise, that means that this problem is also called model measurement as well. Model measurement as well. Okay, that means we are basically trying to calculate or estimate the test MSE from the training MSE, and as well as model selection as well, like what kind of model will be best suitable for our input data or test data. Okay, so and bootstrap is basically helping us to get a fair idea about like accuracy of the parametric estimate. Like we talked about bagging, boosting those algorithms, right, where we will be basically using more than one decision tree to fit a particular problem. Okay, we will see that in future videos as well. Okay, so we will mainly talk about cross validation in this particular video. In the next video we will talk about the basic concept behind the bootstrap. Okay, so to start with, let us try to see what cross validation is and what are the different kinds of cross validation methods available to, okay, in statistical learning. So for that, so we will be talking about cross validation now. Okay, so before we talk about different kinds of cross validation methods available, let me pull out a couple of pictures over here which we discussed in our previous video to recap like what we have seen over there. Okay, now if you see it over here, this two stuff we have seen in my model measurement videos, right? Over there we have defined the MSE, which is nothing but the average value of the predicted value and the actual value and their difference, and squared it. Okay, so and while discussing that one, we discussed a scenario over there, right? So suppose if this small circles are my data points over there. Okay, and we try to fit the data using three different model. Let's say a linear model. If you see this orange color one, okay, this blue color one is a, maybe it's a quadratic model over there, and if you see the green color one, okay, so it is basically trying to fit each and every data point over there. It's a higher dimension compared to the blue color model, right? So we call it flexibility over there. The more polynomial, the more power we are going over there. Okay, so it is more flexible over there, right? And after fitting all these three different kinds of model over there, okay, we draw the graph of training MSE as well as test MSE over there, right? Now if you see it over there, when the flexibility increases, right, so till that point where this quadratic graph was there, it was somehow okay. The training MSE was still below the test MSE, but not very far away. But whenever we are increasing the flexibility over here, the training MSE is going down, because training MSE means the difference between the predicted value and the actual value of that machine learning model, right? So and we are squaring it over here, right? So that means this difference will be very much smaller in those cases, because this particular model is actually touching almost every point over here, right? So if you see, when the flexibility increases, the training MSE goes down, but this model has a very higher variance, because whenever the test data changes, the model will not be able to generalize it much, right? So in those cases, generally the test MSE goes very up over there. That's why the training MSE is not a very good measurement of model accuracy, right, or model performance compared to the test MSE over here, right? Now there are several cross validation methods available to estimate the test MSE from the training MSE as well, because as I told, because there are very limited amount of test data available to actually perform this particular task, apply this particular model on the test data. Because if you think about the real life scenario, like availability of huge number of test data is it's a very big constant over there, right? So let me go down a bit over here. Okay, now let us talk about different kinds of cross validation methods. Okay, so for that, let me pull out a table over here. So there are three different kinds of cross validation method. Okay, one is validation set. Okay, the first method, this is one approach. The second approach is LOOCV. Okay, leave one out cross validation. Okay, cross validation. I will try to maintain the space over here. And the last one is K fold cross validation. Okay, so now these three different methods have their own pros and cons, so we'll try to see that one. First, let us try to understand how they works. Okay, so the validation in the validation set approach, what is happening is basically, as we are planning to estimate the test MSE from the training data, right? That means, so to do that one in the validation set approach, what we do is we divide, let me change the color, we divide the whole training set, okay, into two subset. Okay, the whole training set will be dividing into two subset by randomly choosing choosing training observations. Okay, so that means we are basically dividing the whole training set into two different subset, and when we are doing it, we are basically randomly choosing the observations from the whole training set. Okay, now the first subset or any of the subset, one subset is used for training purpose, training the model, and the second subset, the second one is used for validation purpose. Okay, now validation sets are generally used for model or model selection purpose over here, like this kinds of scenario where you need to choose a proper model for your input data, right? So what you will be doing, like for each and every iteration, so you will be choosing either the linear model or the quadratic model or the higher polynomial degree model. Okay, and divide this whole data set, the training data set, into a training set as well as a validation set over there, right? And you train the model using the training set, and using the validation, using the other part of the subset of the data, you basically calculate the MSE values, right? And for which model the MSE value will be less, you will be choosing that particular model for your data. Okay, now if I just talk about the different drawbacks of validation set approach. Okay, we can think about these things. As we are choosing randomly observations, right? So that means each time I am choosing a particular training set and validating it, right? So each time our randomness is getting increased, right? Because each and every time that training data set is getting chosen very randomly over there, right? So that's why this method is very much variable over there, right? So it's very highly variable actually. It's highly variable. And the second drawback of this method is, as we have seen before, like the statistical machine learning algorithms generally work better when we have a large number of training data set, okay, over there. Okay, so as in this particular method, we are reducing the number of training data set, right? So in that way, the test error we are calculating using this validation set, right? So it is not, it is not that much correct. It generally, it overestimates the test error. Okay, so overestimations of test error. Okay, so this is another drawback, because the we are using lesser number of observations for our training, right? So now to fix this one, another method has been developed called leave one out cross validations over there. Okay, now in this approach, what we do is among all training observations, we leave one, okay, and rest of leave one for validation, okay, and use the rest of the observations for training purpose. Okay, so that means we are only keeping one aside and then using other observations for our training purpose over here. Okay, so if I just write it in terms of in mathematical terms, okay, so if let's say if we have our training data set something like x1 comma y1, x1 comma y1, okay, then comma, I'm just taking single feature over here only. If we have multiple features, then this x will be a vector over there, right? Now x2 comma y2, okay, comma dot dot dot, let's say xn comma yn. Okay, so if we have training set something like that, in the iteration number 1, what we do is, so let us write it down. Iteration 1, okay, so what we are doing it over here, we are basically keeping x1 comma y1, we are basically keeping x1 comma y1 aside, okay, and using rest for rest for training, okay, and after training that model, okay, we are using this x1 comma y1, okay, for validation purpose to calculate the MSE values over there, okay, and after training we are using this guy over here, x1 comma y1, to calculate the MSE, okay. So we are talking about, let's say, regression problem over here only, okay, and the same concept works in classification problem as well, where our target variable is not numeric in nature, okay, it is non-numeric in nature. So that is what do. Suppose let's say in this in this iteration 1, we the calculated MSE is our MSE 1. Okay, so now in iteration 2, what we'll do is we'll do the same stuff over there. Okay, so in iteration 2, okay, so now what we will do now, we will take the second one out and use the rest of the one to calculate for training purpose, and use the second one to calculate the MSE again. Okay, so I'll just copy this one over here. So this time we'll be using x2 comma y2. we are keeping it aside, okay, for and using rest for training, and after training we are using our x2 and y2 to calculate the MSE value. Okay, let's say this time our MSE coming up something like MSE 2 over here. Okay, and we'll be repeating this process n number of times over here, right, because we have total n number of observations over here, right? So if I just copy this whole stuff and paste it over here, okay, so our iteration in will be something like, we will be keeping the xn and yn aside, right, and we will be basically using the rest of the one for training purpose, and you will be using x and yn for to calculate the MSE again. Suppose it is MSE n over here, right? So we have total n number of MSE over there. Now what we'll do, we'll just take average of those MSE values to calculate the final MSE value over there. Okay, so let me go down a bit over here. Okay, so our final MSE value, okay, we'll say cross validation MSE value. So we'll try to write it in this way only, cross validation MSE value. Okay, so it will be something like, as there are n number of observations over here, right, that means 1 over n. Okay, and then we are basically taking the summation of all those MSE values over here, right, in summation n equals to 1. Okay, I'll just say I equals to 1 to n over here. Okay, and then the MSE I over here, right? So this will be the MSE value for this guy, right, for leave one out cross validation method, right? So what we are essentially doing it over here, each and every iteration we are basically taking a single entry, okay, and using that entry we are basically calculating the MSE values, and taking at the last we are taking the average value over there, right? Now think about it, this particular approach is solving the second problem over here, right? So over there we are basically reducing the number of observations, but here as we are only leaving out a single observation, that means most of the time in each and every iteration we are almost using all the training set for the training purpose. Okay, so but the problem is over here is, as we are using the almost similar training data for training purpose, there is no variability, or so performing this guy leave one out cross validation, most of the time it's in each and every iteration it basically creates a similar value. Okay, so similar MSE values over there. So that means it is even though it is solving this problem over here, it is not a very good measurement of MSE over there. Okay, that means the mean square error over there. Now to fix this one, okay, there is a generalized version of leave one out called k-fold cross validation. Okay, so let us discuss that one over here. Now in k-fold cross validation, what we are doing we are splitting the training data set, okay, training data set into k groups, data set into k groups over there. Okay, so if you see it, like the leave one out cross validation is actually a very specific case of k-fold cross validation where k equals to n, right? Over here we are basically splitting the whole data set into in n groups. Basically in each and every group will have a single element over there, right? And then we are taking the single element out and using rest of the elements to for the training purpose, right? I'm repeatedly talking about elements, but basically it's a, I should say, observations over here, right? Now over here also, like in the k-fold cross validation, we are splitting the whole training data set into k groups. Okay, and we keep as we are doing it in LOOCV, we keep aside single group. Okay, and use rest of the groups for training purpose. Okay, and use the kept aside group to calculate the MSE over here, right? So if you see now if I just do this, if I just follow the same approach over here, okay, so instead of n it will be k over there, right? Because this time I am not dividing I am dividing my whole training data set into k groups over here, right? And each and every time I am keeping aside a single group and using rest of the groups for training purpose and calculating the MSEs over there. So if I just write the final MSE, okay, I'll not repeat it again over here. Okay, so instead of n, say MSE, okay, instead of n it will be k over here, and I equals to 1 to k over here, MSEI, right? So this is my MSE output or MSE value for the k-fold cross validation. So yet basically we are after calculating each and every MSE values for each and every group, we are basically taking an average of them over here, right? Now if you just compare these three methods we just now discussed over here, right? So k-fold definitely have a computational advantage over LOOCV, because in LOOCV we are basically having a iteration for each and every data point or observations. We are having a single iteration, right? That means if my data points are very high, that means if my observations are very high number, that means n is very large number over here. So in that case LOOCV will be very expensive to compute, right? So but in k-fold approach generally we choose the k value as 5 or 10 maximum. So that means whatever be our n value, that means whatever be our number of observations over here, we generally divide the whole data set into either 5 groups or 10 groups max, right? So k-fold definitely has a computational advantage over there. Now apart from computational advantage, there are certain other factors also we need to consider before we apply any kind of method, right? And basically I'm talking about bias variance trade-off over here. Now if you remember from my previous video, I talked very extensively about bias variance trade-off over there, right? So whenever we want to choose a particular model or particular method or particular machine learning method over there or algorithm over there, right? So we basically talked about the bias variance trade-off over there, right? We basically choose a model which is having a less bias and less variance. That is the ideal scenario over there. If that is not possible, then we have to take a trade-off over there, right? So there is a concept in over here as well between among these three methods over here. Okay, now if we just think about in terms of bias over here, right? So this variable set approach is basically highly variable. That means we are randomly dividing this whole training data set into two subsets over here, right? So it's a highly biased over there, because each and every time we are working on a very random data set over there, right? Now think about LOOCV over here, right? Now each and every time, each and every iteration, we are almost taking the same data set to train the data, right? So that means the output is also almost similar over there, right? So it is, we can say it is very unbiased. So if I just write it down over here, this is highly biased. Okay, this is highly biased. Now applying the same concept over here. So if I just go down, so this method is, let me change the color, or let me keep it in the same color. It's very unbiased, right? Now as each and every iteration, we are also taking that all the iterations average over here. So almost the CV or the cross validation MEC value is almost same as each and every iteration MEC values over there, right? Now if I just apply the same logic over here for k-fold, its biasness will be somewhere between this guy and this guy over here, right? So biased somewhere between validation set and LOOCV, right? So bias, I'll just mention bias. Okay, so in terms of bias, k-fold is actually standing in between them, right? Now if I just apply the same logic in case of variance over there, right? Now what do you mean by variance? Variance means, suppose we are training a machine learning model with a data set, right? Now if I just change the data set, and if there is any very extensive change in the output or the prediction of that machine learning model, we said that particular model is very much highly variance model, right? Now think about this guy over here, LOOCV. Now each and every iteration, we are applying the same logic over here, right? So each and every iteration, we are almost dealing with the same training data set, right? So that means in terms of variance, this particular method will be high because the outputs are correlated over here, right? Because every time we are using similar data set over here, right? So that means in terms of variance, it is very high variance over there, right? Now if I just talk about k-fold over here, so again, as we are using k groups over here, right, compared to LOOCV, these outputs will be less correlated over there, right? So that means its variance is lesser than LOOCV over here, right? So if you see it over here, like in terms of bias variance trade-off, also this k-fold always give better estimate because its variance is somehow lesser and its bias is also somehow in between these two guys. That means somehow okay, because we cannot choose a model which is fully unbiased and very high variance, right? So generally k-fold performs better than compared to these two other methods over here. Okay, now think about this one. We generally talked about this MSE values over here because most of the times we were talking about the regression scenarios over here, right? That means our target variable is numeric in nature, right? What about our target variable is not numeric in nature, right? So basically we are talking about the classification type of problem, right? So the same concept goes for classification type problem as well. Okay, so over there, just the way we are calculating MSE, that will be changing. Okay, so if I just talk about in terms of classification, okay, say if you just write it down over here, something like this one, CV for classification. Okay, so it will be something like, so how do we measure that one? So we because of the non-numeric nature of of its target variable, right? So we cannot measure the MSE something in this way, right? The output minus the, if I just show you over here, we cannot apply the similar formula over here, right? So what we do for generally for classification problems, we basically determine the number of misclassified observations. Okay, so if I just talk about LOOCV, every time we are only having a single observation for our testing purpose, right? So that means whether it is our model is able to successfully classify it or not. So based on that, we are taking that number or not, right? So if I just mention error, okay, error as error I, that means the ith iteration over here, right? So if I just mention error I as the ith iteration, how many misclassified observations are there, right? And if I just sum them up based on let's say I equals to 1 to n, because we are, if I just talk about in terms of LOOCV, there will be n groups over there, right? And if I just take a average over there, that means 1 over n, right? So this will be the MSE value of the classification over there, right? So if you see, just this formula is getting changing over here, where if I just make it very specific, right? So where ERR I, okay, so this guy will be, let's say, some values I, where our y underscore I, that means our actual value, right, is not equals to the predicted value, right? Predicted value generally we mentioned it as yi hat, right? Hat, then yi, right? So this is the condition. Basically, when it is satisfying that condition, that means we are basically finding the data points where we have done the misclassification, or it did not did the classification correctly over there. Okay, then we are summing them up and taking the average over there. Okay, now we talked about very briefly about all these different cross validation method over here, right? And we also saw like which method will be used and when, and which method is more useful over here. Okay, in the next video we'll talk about the concept of bootstrap, okay, which will be helpful for our future videos, like when we talk about other decision tree or basically ensemble methods, like our bagging, boosting, those stuff over there. Okay, hopefully this video is helpful. See you in next video.